All right. Good morning. We're starting into the section 4.4, first derivative test. And I want to, typically when I've taught this, sometimes you start with all the terminology and what the rule is and the words and stuff. And I can think it can be kind of cumbersome. I think I found it better to work through an example and you get the gist of what the first derivative test is proposing doing. So I think that's what I'm going to do here. And afterwards, I'll go through the actual wording of the situation and see the words themselves and show you that on some slides that we have. But right now, I want to do from section 4.4, problem number 13, which is f of x equals x to the third minus 6x squared plus 2. We're running the first derivative test. So what we're trying to do is to find whether the local extrema are maxes or mins. And by definition of the situation there, it is a matter of, in order to do that, we need to determine, first of all, what the critical points are and go from there. So part of the situation is going to be to, first of all, take the first derivative and find the critical points. Set it equal to 0 and find out where our critical points are. So let's do that. So I'm going to start with taking the derivative of this function, which is f prime of x, equals 3x squared minus 12x. All right, with that, let's factor that down. We're going to find out what causes it to be equal to 0, so a benefit will be realized by factoring this. I see a 3 is common and an x is common. So that ends up giving me x minus 4 as one of the factors. So the derivative of this in this situation, let me go ahead and move it over just a little bit. So the derivative in this situation is 3x times x minus 4. And you'll see in a minute why factoring sometimes can be leaving it in factored form can be an easier way to address whether the answer is going to be, we're concerned about whether it's positive or negative here, whether the slope is increasing or decreasing in particular intervals. So leaving it in factored form allows us to do that. So what I'd like to do now is find out what causes this thing to be equal to 0. So the circumstance is, let's see, let's set this equal to 0. And that can happen when 3x equals 0 and when x minus 4 equals 0. X equals 0, x equals 4. So those are our two critical points in the circumstance here that we're dealing with. So what I want to do is I'm going to draw a number line here and show the two critical values, 0 and 4. And what I'm concerned is about the region to the left of 0, between 0 and 4, and to the right of 4. And I want to get a sense of, is it increasing or decreasing on those intervals? So again, one of the things you can look at when you go back to the original function is to see that f of x, a cubic, you know that x cubed looks something like that. And when we've got the extra term in there, the minus x squared, 6x squared, etc., that gives it a little bit of a contour. So we probably got a shape like this. And the main thing is, because it's positive x cubed, it's going down when we go, x goes to the negative direction, and it's positive upward when x is going in the positive direction. So that's going to be consistent with what our answer will be. And in the future, it'll be good to think about that. But anyway, what we're doing now is we're going to check the regions to the left of 0, right of 4, and in between 0 and 4. So we pick a number that's easy to work with, a negative number, small negative number. So -1 will be at our disposal. We can choose that and pick that. And then 1, 2, or 3, 1 usually is an easiest number to work with in that situation. And to the right of 4, a smallest integer that we could get would probably be 5. And again, picking integers every time here is what we're working with, but there's going to be some situations where you can't pick an integer, like if you're between 0 and 1. I'm going to do a problem in a little bit that shows that. And you got to pick a fraction or a decimal in between 0 and 1. So that's going to happen. But if you can, pick numbers that are easy to work with. So I've got -1, 1, and 5. So what I'm going to do is plug those into the derivative function. So I'm going to plug in -1 first. So we'll do this one first. So f prime of -1 equals 3, and so that'll be -3, right? Times -1 minus 4, which equals -3 times -5, which is -15, positive 15, excuse me. So that is positive 15. This is positive 15. This is a positive value over here, so the slope is going up. That's the idea. All right, let's go to the next one, f of 1. So f prime of 1. This time we get 3 times 1 minus 4. Notice the signs again. It's 3 times minus 3, which is minus 9. So we got a minus 9, and the slope in this case is going down. Okay, the big thing is that it's positive here. It's negative here. Let's see what we get in the last one. So when we plug in 5, f prime at 5, we end up with, what is that? Positive 15 times 5 minus 4 equals 15 times 1 is 15. So that's positive 15. So again, we're going up, and that turns out to be a positive value. Okay, so now the situation is that we just need to make a determination. When you're at the critical values, is it going to be a max or a min? So when you look at, for instance, the first one at x equals 0, this circumstance here, that what you've got is, when you're to the left-hand side, you've got a positive slope, so it's going upward. And when you go to the right, it's going downward. So at 0, it was actually at a peak. So we end up with a local max. Local max is at x equals 0. All right, and then when you come over, look at this situation, we've got negative slope to the left and positive slope to the right. So when you look at this circumstance, they come together down there at local min at x equals 4. So the terminology is going to be important here. We got a local max at x equals 4. It's going to be in local min at, at a local max at x equals 0 and local min at x equals 4. That's going to be important, but we're also going to need what the value function is. What is that local min and what is that local max? So along with that, we also need to do a calculation of what the values are. So we go back to the original function here, which is x to the third minus 6x squared plus 2. Let's plug in the value 0 into here and see what what the local max actually is. So we end up with 0 minus 0 plus 2 equals 2. So we end up with the coordinates of the point are, you plug in 0, you get 2. So that, okay, and then for the second one, we've got f of 4. You get 4 cubed minus 6, 4 squared plus 2. That's a 64. That's 16 times 9. I guess that's negative 96 plus 2. Negative 32 plus 2 equals negative 30. So we end up at 4. We've got negative, we got negative 30. 4, negative 30. All right, so in words, let's say this. So the local max is, what is the value of the local max? It is 2 at x equals 0, and local min is negative 30 at x equals 4. All right, so that is the outcome of the situation here. And it's a matter of realizing that when they come together up at the top, like this, at 0, we've got a local max. When they come together at the bottom, we've got a local min. All right, that's one of the key things. So that's an example of where that comes from. What I want to do now is I'd like to talk about, just really briefly, what the words actually say for this circumstance. A little more complicated. Let's go to that situation right now. So what I want to do is, let's see here. So what I want to pick out the wording of the situation. So let me get it to full screen here. Okay, so for the first derivative test, you can see what it's saying there. And you picture what we had there for the diagram. We had the max was at 0, up at 2, and the local min was at x equals 4, down at negative 30. Down at negative 30, up at 2. But we were at x equals 0 and x equals 4. So in this situation, the critical value C that they're discussing here are is the 0 and the 4 from our previous problem. So let's take a look at, suppose 0, for instance, is a critical number of f, and 0b is an open interval containing 0. So we're going from to the left of 0 and to the right of 0. And when you go to the left, if you go all the way down for the, if f prime is greater than 0, when you go to the left of C, when you go to the left of 0, when the slope is greater than 0, which was our situation, and when you go to the right of 0, when C is 0, when you go to the right of 0, which means it's saying the slope is less than 0, which means it's going down, then you have a max at 0 because it was going up from the left and down to the right. Therefore, it's up at a max at C, which is 0. And then when you go the second part, when you got a minimum value, our C was equal to 4. So the idea there is that when you're to the left, A to C, of 4, we had negative slope coming down. And when you're to the right, it was positive, going from C to B, whatever our interval was. It's positive, so it was increasing. Therefore, to the left, it was coming in down. And when you're going off to the right, it's going up. So it was at a minimum, at a bottom in that situation. Therefore, you've got a local minimum value. Now, notice what the bottom statement says down here. The idea here down here is that if you've got the same sign on both sides of C, then you don't know. Well, you do know. Then you do know that there is no max or min in that situation. So the circumstance is that you don't have a max and min. If it's coming down, then it continues to go down. And if it's going up, it continues to go up. So you don't have a max or min. Then, yeah, that's what you don't have, a max or min. So that is the situation there. And I've got some other problems. I'll be talking to you in just a little bit about a few other things regarding the first derivative test. Hope you're well.